Great, so today I'll be talking about experimental data assimilation for multiscale turbulent fluid flows. So as I understand it, this is a pretty diverse audience. So for the non-fluids and turbulence folks, I'll spend the first couple of minutes trying to motivate what turbulence is, what the complexities are, and how that translates to challenges in extracting measurement data from turbulent fluid flows. So, so the main motivation here is we're looking at turbulence separated flows. So these types of flows exist in nature in a variety of different contexts. So over here, since I'm an aerospace engineer, my bias is towards aeronautic flows. So these are the types of flows that you will see when an aircraft undergoes takeoff and landing and whatnot, or when the pilot undergoes complex maneuvers. And at these stages of flight design, these are usually the limiting factors, because these flows are extremely complex and difficult to predict or simulate. So this often ends up being the most expensive and challenging factor in aircraft certification. So, here's the flow separation right there, which basically means that the flow is lifting off the surface. So this is really bad for aerodynamic efficiency. It creates things like drag and increases power and fuel consumption and whatnot. So what are the actual challenges for these types of flows? It stems from two things. Number one, it's the inherent complexity of turbulence itself. It is multiscale, it is a strongly nonlinear system, it's highly three-dimensional, and highly unsteady. So these are all complex factors that I'll delve into a little bit more in detail. Because of this inherent complexity of the underlying system, there's data sparsity in measurements. It's really difficult to extract all the different variables, frequencies, and dimensions in our flows. If the 3 dimension is unsteady, we need to ensure that our sampling systems can sample fast enough to resolve temporal frequencies and also captures more complex spatial features as well. So, to motivate what turbulence is, I'm going to talk about a specific feature of this, which is the multiscale nature of turbulence. So, I have to start off with this equation. These are the infamous incompressible Navier-Stokes equations. It describes the governing equation of a fluid particle moving in space. Okay? First one is the conservation of mass. Mass in equals mass out. That's the statement. U is the velocity flow field, and it's a three-dimensional flow field, right? So you have velocities moving in x, y, and z directions. And you've also got the momentum balance. So I'll explain what this is. So you have the pressure term here, P, and you have Reynolds number, which is a dimensionless number that describes the ratio of the viscous or inertial effects to the viscous effects of a local fluid. Now, from a dynamical systems point of view, you can view this by just rearranging this equation, right? You're looking at the system evolution versus time. So if you just want to move the time derivative term to the left-hand side and the rest of the terms to the right-hand side, you now have, so it's a df dt equals some sort of operator that evolves the flow field in space. And this evolution equation can be parameterized by this Reynolds number. So in principle, you can think of this Reynolds number as a bifurcation parameter, for those of you who are familiar with that, wherein if you increase the Reynolds number, you increase the nonlinearity of the system, or increase the degree of chaos in the system. Specifically, the Reynolds number leads to an increase in the separation of scales. All right, so I'm going to introduce the concept of scales now. So this is a direct numerical simulation of a turbulent flow over a flat plate. Pretty basic flow, nothing super fancy, but it's rich and complex. With the frame count, we see an increase in the Reynolds numbers. And what we see right away is with larger and larger Reynolds numbers, you have more richer representations of scales. So you have large scales. You also have smaller scales near the wall. This brings us to the energy cascade. Okay? Basically, you have a whole distribution of flow structures. You have large-scale eddies that dominate the energy. They contain most of the energy in the flow. And this energy is being continually redistributed to smaller and smaller scales. Okay? And these scales basically contribute to viscous dissipation to heat. So the point is as follows. With high Reynolds numbers, we have large-scale separation. Why do we care about this? In industrially relevant flows, so like in aeronautics or whatever, the Reynolds number can be on the order of 10 million. In other words, the largest scales are separated by the smallest scales by a massive number. So to simulate these flows via computers, we need to form like a grid, a computational grid, and to resolve these small-scale features, we need a super fine mesh, right? And for industrial relevant configurations, this mesh can be extremely refined to the point where to simulate the entire flow, it could take several years to simulate on a supercomputer. So in industry, what really happens is they resolve just the large scales and model the effects of the small scales on the large scales. And they push this envelope a little bit further with something called LES. Still gets it somewhere, but these still take several months to simulate on a supercomputer, so it's not efficient. So in industrial relevant configurations, we have much higher numbers. So if we want to push the envelope further, we need experiments. Okay. However, at high Reynolds numbers, the flow presents other practical engineering issues for experiments. So first of all, at high speeds, we only want to image the flow through fluid imaging devices. Usually, we can't sample fast enough to resolve the timescales. So this leads us to the well-known issue of aliasing, wherein you just don't sample fast enough, and higher frequencies incorrectly manifest as lower frequencies in the spectrum. Second of all, the flow is three-dimensional, right? So this is an example of a flow over a hill, a speed bump, effectively. And I'm showing you two-dimensional slices over the three-dimensional geometry. Ideally, we can get a full global volume, like a volumetric representation of the flow, but that's not practically possible. So we have this sparsity. So we have good spatial resolution, like locally at each slice, but these slices don't sample in time quick enough. So we have low temporal resolution. However, we complement these data sets with sparse sensors. I've noted them as these purple dots on the wall. And these usually measure things like wall pressure. Because these are point sensors, they can sample really fast. So you have really fast time rates, but you have a sparse array of sensors. You can't have like 10 million sensors. It's practically not possible. So we have poor spatial resolution. So we have this trade-off, right? We have the imaging slices that are non-time resolved, but good spatial resolution, and you've got the time resolved information. So we have a bunch of trade-offs. Now the goal here is to complement the two. So here's the objective, is given these time-resolved sensor signals and non-time resolved PIV data, can we actually synthesize the two data streams together to reconstruct information and understand the flow? From a practical standpoint, this means building an estimator. So the input to the model would be time-resolved sensor information, and the output would be a volumetric representation of the flow. Right? Can we do this? The impact is could be quite staggering. We could implement these estimators to build something like a digital twin, where you have a virtual replica of a physical system. So this could be really interesting for real-time engineering diagnostics. Of course, this also leads to a better understanding of the flow, so we can have improved models that we can inform CFD or computational practitioners. Okay, we need a framework to establish ourselves. We have turbulent separative flows in many different scenarios, but we need to choose specific data sets to work with. So under the Boeing framework, or the Common Research Model framework, we have a couple of data sets that we'll work with. The first one is the Boeing speed bump. So you might ask, why are we dealing with bumps when we deal with aircrafts? It turns out Boeing designed it specifically to emulate certain flow characteristics that you would see in high liquid winds. Okay? So these are experiments conducted here at UW. Upcoming experiments include the Common Research Model that will be conducted inside the Person wind tunnel. This is a pretty large-scale facility, 8 by 12 feet in dimensions, and you can see the staff over there. So you actually are standing inside the test section. So it's a pretty large-scale facility. And the idea is to add these data sets to a database where we can benchmark machine learning models, reduced order models for turbulent flows. Because that still really doesn't exist in a comprehensive sense for experimental data. All right, so what are the types of measurements? So the first one I showed you was fluid imaging. So this is particle image velocimetry. We're trying to extract velocity flow fields of a fluid flow. So this is a model inside the test section of a wind tunnel. So you have flow moving out of the page from left to right, let's say. You have a laser system on top, and you have a high-speed camera that's synchronized. And effectively, it produces a movie. Well, this is post-process, of course, but you have snapshots of a two-dimensional, two-component velocity flow field, called that as 2D, 2C, of the PIV flow field. There are techniques where you can get the third component, so you have two-dimensional slices, but you can extract the X, Y, and also the out-of-plane component of velocity as well. So this is one type of data set, and you could repeat this at multiple planes like I showed you before. And you could also have unsteady wall pressure sensors. I've shown this as well. Something that's ongoing is we're trying to extract skin friction streamlines. I won't go into this in detail, but it gives you a pretty well-resolved idea of what's going on at the wall locally. Okay, so here's the objective. We want to address 3 major data assimilation challenges. And I've covered quite a bit, so I'll just summarize it over here. Number 1 is to super resolve or upsample these PIV images. So if you take a look at the movie here, you have these snapshots in time, but they don't look related to one another. Even though they're ordered in time, they don't sample quick enough to resolve things like the motion of vortices and whatnot. So we want to try and upsample this. So I'll talk about this today. We also want to infer unmeasured variables and dimensions. So things like, if you're just given 2D, 2C, so 2-component snapshots, like the movie here, how do you get the 3rd component? Because these flows are 3-dimensional, so that all 3 components influence the dynamics. 3rd, how do we get the pressure from velocity? I'll talk about this as well, and how do we integrate that into a single framework? Second, the 3rd, which would be the holy grail, would be to try and get a volumetric reconstruction of the entire flow, given the sparse sensor measurements as inputs. Okay. Of course, we need to constrain these models. So number 1, it has to handle multimodal sensor inputs, so different types of sensor data. So wall pressures, the skin friction maps that I mentioned earlier, and whatever system actually, whatever data you have available as sensory inputs. The models can't be fully data-driven because the underlying system is deterministic. You have rules to this, right? I showed you the equations there. So we need to constrain these predictions somehow through physics. How do we do this? And ideally, these models are generalizable and interpretable, but that's an ideal case. Okay, so we'll talk about the first case where I'm going to try and upsample or super resolve these rules. Okay? All right, so I'm going to try to describe what the bump is. I mentioned what this is before. It's designed to specifically replicate high-lift wing configuration flows, so turbulent separated flows. It's basically a speed bump, so a Gaussian hill, you extrude it and then taper on the sides. Okay? Turns out this flow is very complex. It's 3-dimensional, it separates, and it's highly unsteady. Okay, so it has all the characteristics that we would see in an actual turbulent separated flow that you would see over an aircraft, for example. All right, here's the flow case. We have the same setup. The flow speed is at 45 meters per second. Reynolds number at 226,000. And the PIV system, so the laser system that images this, is 200 millijoules per pulse. So to give a physical perspective on this, it's a really high energy laser. It's a class 4 laser, and it has a maximum repetition rate of 15 hertz. So that's a hardware limit. It's pretty common in a lot of these applications. So we're sampling at 40, the flow is going at 45 meters per second, but fairly fast. But we're sampling at 15 hertz, so we're going to lose some dynamics. We're going to get some aliasing. This is what we saw in the movies earlier, right? The goal here is to upsample the fields from 15 hertz. So I show this, this diagram where the colored snapshots are what you measure, and what we want to try and estimate are the ones in between. Okay, that's the goal. So from 15 hertz to ideally 2,000 hertz. All right, so I'm going to address this undersampling issue. So we begin with a time series of measurement data, PIV measurement data, and the snapshots in gray are the ones we want to predict. How do we do this? We use pressure sensor information at the wall, so these are the 4 dots you see in the first colored image, and we oversample them. So I mentioned that these pressure sensors can be time resolved, so they have really fast sampling rates. So we sample those and synchronize them with the images, as denoted by the vertical red lines. And the idea here is to leverage the available time-resolved dynamics in the sensor space, green, to try and fill in the gaps in the image, the PIV image domain. Okay, so that's the overall goal here. So here's the setup. I'm looking at the centerline part of the bump. Here's the PIV flow domain. And the dots, black dots, are the pressure sensors, okay? And this is the raw PIV image that you would see at 15 hertz. It's completely uncorrelated. Data that I have, 2-dimensional, 2-component PIV, sampled at 15 hertz, and this is synchronized with the 9 wall pressure sensors at 31,000 hertz. So it's a few orders of magnitude difference, and we synchronize it using a laser's pulsing mechanism. All right. So I'll provide an overview of the actual architecture here. So we start off with our series of undersampled PIV snapshots. Now, these are high-dimensional images, right? I mentioned that turbulence is multiscale, it's high-dimensional, and it has really large separation of scales, so it's high-dimensional. We want to compress it somehow. The first step is dimensionality reduction, and we choose to use a linear PCA. There's a reason for that. It goes by many other names, proper orthogonal decomposition, or just a singular value decomposition, effectively. From our perspective, what it does, it splits it up into two spaces. So these would effectively be your right and left singular vectors. You want to think about them like that? Where the right singular vectors would be the POD bases, basis functions effectively, and the corresponding coefficients, which I denote as A over here. So effectively, these coefficients modulate these bases vectors in time to describe how it evolves, how the flow field evolves in time. In other words, the coefficients are functions of time, and they're undersampled. So I try to show them over here through these dots. And now we want to upsample this effectively, right? So we synchronize them with pressure sensor data, which are time resolved. We do have the high frequency information here, and we build an estimator. Okay? The idea is to establish a map that takes us from the wall pressure sensor state to the state of a latent state, a latent representation of the PIV flow field. Okay? Specifically, take the note of the notation over here. We're using an LSTM to build this model for now, and we provide a historical sequence of pressure sensor information and ask the model to predict the latent representation of the coefficients. And the ansatz over here is that this map should hold, if trained well, should hold for any pressure sensor state that you feed it, right? The loss function is just the mean squared error between predicted coefficients versus the ground truth information, which we get over here, and we build an estimator. For inference, we feed to it time-resolved pressure sensor data, and we just apply the model to it and shift it in time. And we get a time-resolved estimate of the coefficients, and because the modes are orthogonal, right, where we have SVD, singular vectors and whatnot, the projection is orthogonal. And we truncate it to some rank R, and we can get our full-dimensional full field snapshots, which are time-resolved. Okay, this is the idea. And of course, we truncate it to estimate, to resolve certain nonlinear features. For those of you familiar with this, I'm trying to resolve the Reynolds shear stresses. All right, so these are the different modes that we get, but I specifically want to direct your attention to the spectra on the right. So we have different modes here, and the dotted red line shows what you would get from the original under-resolved data. So these are a frequency spectrum, and you don't really see anything, right? It's basically a line, but the black lines are the estimates from the time-resolved spectrum. And you can see we can actually get some really nice humps over here that resolve some actual physics. So that's, we could also resolve the humps a few orders of magnitude higher than what we were able to get from our input data as well. And each of these modes corresponds to an actual physical process. So just to illustrate this, these were the original snapshots. They look completely uncorrelated. And here the upsampled, the upsample result at 2000 hertz. You can see we can actually reconstruct the evolution of vortices, the development, and the convection along the shear layer. So these are pretty nice physical reconstructions of what we could get. So here's an idea. This model does come with some issues in that we get pretty poor reconstructions of the estimates at the original sampling rates. So we look at this metric, and we're trying to see the errors associated with each modal prediction. So we have different modes, A1, A2, up until A, K, whatever, and we look at its the histogram of their time distribution. Okay. The point here is that most of the errors are concentrated to 0, so the individual modes are predicted pretty well. However, when you start to accumulate the modes together, errors start accumulating as well. This tells us two things. Number one, the errors associated with each modes are independent and random, actually. And once you start to accumulate these random and uncorrelated errors, they tend to be out of phase with respect to each other, and so you get a pretty non-physical estimate with respect to the error at the end of the summation. However, I don't mention this here, but when you average out these fields to get statistical moments, these modal errors actually tend to zero, average out to zero. Now, this is inherently a limitation of the basis functions in that we are constraining them to be orthogonal, right? Because they're singular values, singular vectors. By construction, the SVD is orthogonal. But recall from the first few slides, we talked about the scales of motion and turbulence. They interact with each other. They're not necessarily independent of each other, and they could interact nonlinearly. So we need to relax this orthogonality constraint somehow. So a solution we propose is to use a nonlinear basis, right? That can actually capture these intramodal scale interactions that we should expect to see in real physics. This relaxes the orthogonality constraint, and we can also get some more interpretable features from this as well. Second one has an inherent issue with the problem setup. Recall what we were doing before. The input was a historical time series sequence, and we asked to predict the PIV frame at a future time series. However, we know that the wall pressure field, measured by these signals, they encode signatures of flow structures about the wall, right? Flow structures are convecting, and you can actually, the pressure field will actually feel the effects of these flow structures. This model does not accurately capture, or doesn't explicitly capture, the convection of those vortical structures until it reaches the final frame. In other words, what I'm trying to say is, we need to predict the intermediate frames as well, okay? Unfortunately, we don't have ground truth information for these intermediate frames because we don't have time-evolved PIV data. So we need to anchor these intermediate frames to some physics so that it actually captures important physical phenomena like advections, or even rolling of vortices combining and amalgamating, making larger and larger vortices and whatnot. So the next couple of slides, I'm going to go over the proposed hybrid framework that we're working with, which is physics informed. So here's a problem statement mathematically. So we have our sensor inputs, which is just a historical series of wall pressure inputs, and we use n sub p to denote the number of pressure sensors that we use. The sequence to one formulation is, just as before, we have a historical sequence, and it predicts one PIV frame in the future. The second sequence, the sequence of sequence model, it's pretty obvious why. We have a sequence of historical pressure sensors, and we try to predict a time-shifted version of the PIV latent evolution. Right, and for the rest of the presentation, I'm just going to focus on the sequence one. All right, so here's the overview of the proposed framework. So to address the first issue, where we want to relax the orthogonality constraint, we build a nonlinear basis. A simple way to do that is just to build an autoencoder, right? This is a pretty generic illustration of what an autoencoder is. I'm sure most of you are familiar with that. We're going to be testing it on a data set of a turbulent boundary layer. For those of you who are familiar with this, it's a DNS simulation of two-dimensional and three components. We have access to all three velocity components. And this is a result that we got by using a vision transformer on this data set. So it does a pretty good job, but just a side note, these things are pretty inefficient to train and pretty sensitive to things like patch sizes and whatnot. So there are much more efficient options to auto-encode these types of high-dimensional flow fields. But I won't get into that in this talk. So now we have an embedding, like a latent representation of the PIV, and it's a nonlinear basis. And hopefully, the features are more interpretable than before. Okay? And now we got to fuse the sensor information to the PIV space. Right? So we first process the sensor signals, which we didn't before, by the way. Right? We pass it through a transformer encoder, and we get a token representation of the sensors. It is an abstract representation of processed sensor time series. We're then going to fuse it with the PIV tokens that we got from the previous step using a cross-attention block. And then we get fused tokens. Then we can aggregate and reshape, and we're going to get an output token. It's a global latent representation of a sensor-informed evolution of the PIV flow field. Okay, just a pretty abstract representation. Then we pass it through a decoder. All right. We project it first, and then first we're going to pass it through a volume expander module, where effectively what I'm trying to do is, remember we were starting off with 2D slices, but the flow is three-dimensional, and the governing equations require you to compute gradients in the outer plane dimension. In other words, we need some volume. So what I'm trying to do here is I add virtual slices in front and back of the measurement plane, completely data-driven. And then I upsample it to a number of weights, units or whatever, and then I also do a channel mapping, where if I have 2D, two-component velocities, I try to extract the third component as well. And I can use this using a 3D convolution effectively. And at the end, I get a 3D, 3C thin volume representation. Right? And a thin volume is enough for physical reasons, but the point is as follows. We can enforce physics here. From the first mass conservation equation, this is in differential form here, I can actually back out the W component, which is the third velocity component that we didn't have access to begin with. Okay? So now we can actually enforce it directly. Second, we still need the pressure gradient. Thankfully, we have all the terms we need now to back out the pressure. Right? So we can directly just get that by just isolating the pressure in the governing equations. And you have a bunch of these gradients, right? You have a time derivative here. Since the model outputs a sequence, you can just use finite difference approximations to get the time derivative. Same thing with the spatial gradients as well. Okay? And these gradients are approximated by finite differences. So you have fixed kernels and fixed convolutions. So this process does not have any learnable parameters. It's directly solving for the pressure gradient field, which is really nice from a compute perspective. Now we can just plug that into the residual of the momentum, and now we have a new loss formulation for the momentum balance. So we've now been able to enforce softly the mass balance and the momentum balance for the entire sequence. Okay. Just a bit of a bonus, we can integrate the pressure gradient to get the actual pressure field, which is important for a lot of people. But we do this through differentiable layers, and we numerically solve it. Again, there's no learnable parameters in this branch. However, because it's done on a GPU, the solver must be highly parallelizable and must only take a few iterations. So for those of you who are familiar with numerical methods, we solve this on a 3D Laplacian grid, effectively. But the Laplacian operator in the Poisson equation is symmetric positive definite. So we can use that and use things like Krylov subspace projection methods, like conjugate gradient iterative method, to try and solve for the pressure field. And the solver, because it's iterative, it's unrolled. In other words, each iteration becomes another differentiable layer in the computational graph. So for the loss function, you can just backpropagate these gradients to the inputs. And of course, this is pretty important from a physics perspective. You can't have the model generate any random solution. It has to be unique. And in physics, we do that by imposing very well-posed boundary conditions. Over here, we can directly enforce pressure boundary conditions as hard constraints. All right, the final loss is as follows. You've got the data mismatch, the continuity losses from mass conservation, the momentum conservation, and things like the pressure recovery and other boundary conditions as well. Okay. So, with the conclusions, we've been able to propose a hybrid framework to tackle several issues like temporal resolution, physics constraints enforced, and inference from unmeasured variables and whatnot as well. We're going to have upcoming experiments to build our database to really exploit these methods and demonstrate their capabilities for estimation. At this point, I'd like to acknowledge my collaborators as well as some funding agencies who pay me. So there's Boeing and the Natural Sciences and Engineering Research Council of Canada. I'd also like to acknowledge the Herbal Fellowship, which I received in 2023. And this is also, I guess, like an advertisement for people over here. So this is a fellowship for, I believe, master students and early doctoral students who study and do research in data science and computation applied to engineering. I think I got that right. Okay. And I think a deadline is coming up mid-May or something, so keep an eye out. All right, thank you, and I'll take any questions you may have.
Kevin, that was great, and thank you for explaining what the fellowship is and mentioning the upcoming deadline. Please, where they can find information? Like where's the?
I got an email from my department.
Okay. Okay, if you're interested, I can look it up and see where you can apply and send an announcement to the campus. Great talk. So if Kevin can explain more or can address any questions, you may have, please raise your hand and let's discuss your research.
Yeah, I noticed it seems like there's a lot of parallels between this research and the multi-frame generation that NVIDIA came out with a couple of months ago. Are there any parallel or inspiration that was happening about the time of research?
Not familiar with the multi-frame generation. Could you describe what that is?
From like a video game's perspective, visually each individual frame that basically simulating additional frames for added smoothness.
Oh, I see. Okay.
And pressure and that sort of
Yeah. Well, I mean, the inspiration for all of this comes from the actual physical challenges that we have, but it's great that NVIDIA is working on this as well. The issue with that is, I mean, for a lot of those models, like video generation, right? If you have low frame, like FPS, low FPS, you still have some sort of correlation from one frame to the next. In these systems, you completely lose the correlation, which is why we need complementary data sets like the wall pressure sensors that encode some of the time resolved signal frequencies. So, yeah.
So I'm not in like aeronautics or what have you. Could you explain like an application of this? Is it like you would model this and then subject parts to it? Like I just was curious how this goes into like industry and what they're interested in.
Yeah, great. Yeah, great question. So fundamentally it would be on using sensor-based estimators. So I guess a needed application would be for something like flow monitoring, doing diagnostic tests, and maybe even have a digital twin. So this is where you would have a virtual replica of a physical model. So let's say you want to do wind tunnel tests, which is how you would sort of certify all these things, all these different types of flows. So you would have a physical model, but also a virtual replica of it. And usually when you try to certify these models, you sweep an entire parameter space. So like the aircraft goes through different pitches, different sort of turn rolls and angles and whatnot, and the flow is different. But if you can build an estimator that is robust enough and generalizable enough, you can just replicate it virtually instead of trying to simulate it using experiments, because these are very expensive to run, these tunnels. The second one would be flow control. Now, I mentioned that the flow is separated here, and when the flow separates, from an engineering perspective, it creates things like drag, which means you need more fuel to actually push through the air. So it increases fuel consumption and whatnot. And you have other issues like vibration noise and other issues. So one possibility would be to try and predict when turbulence occurs through these estimators, and then maybe have a control system to actuate the flow. And there are multiple ways to do this. You can have like suction and blowing of air locally on the wall to try and suppress and then basically bring this, close the separation bubble practically. Yeah.
Giving like inspirations like Steven Sturgout or
Oh, yeah.
like this guy.
So I guess with nonlinear dynamics, I mentioned that the Reynolds number is a bifurcation parameter. One thing that would be really cool is to sweep this parameter space. So it turns out that if you lower the speeds of these flows, you get a completely different type of flow altogether. But if you vary the different, like the geometry, so this is a speed bump, right? If you like make it sharper and sharper, so it's like more of a pointy hill, the flow is completely different. And that is actually like a parameter. And you end up with these bifurcation regimes, where the flow inherently splits up into different types of paths, and the unsteady modes that you see are also very different. So if we can sort of generalize this estimator and build dynamical models, we'll be using something like Cindy, for example, we can actually get these bifurcation diagrams. That would also be super informative. Yeah. Questions?